Hi, today I'm going to start to talk about the distributed load. So far, all the problems that we looked into that and all the forces we looked into that was a single force that was applied on that single point. But there are lots of cases that we have a distributed load rather than have a single force applying on an object. For example, one of the example I can say as a distributed load is the air pressure. If you look at, for example, our body or anything around you, the air pressure will apply on every point on the surface of the object or on the whole body of people. Similar to that, another example we can assume the submarine. When the submarine dive under the knees of the water, then the water pressure would be applied on the whole surface of the submarine. So the whole surface of submarine will be there is a force act on that. So that's the water pressure this act on that. Almost most of the cases you look at, for example, when you assume about when you're standing, the surface of your feet is intact with this with the ground. So there's your weight would be distributed on the surface of your bottom of your feet. Similarly, when you sit on the chair, the weight of your chair or the action and reaction between your body and chair would be a distributed force between your body and the surface of the chair. So there are lots of cases that we have that we can say there's a distributed load, and we need to work with those distributed load. When we are working in the real object in 3D, the distributed load is mostly like a pressure. So it's applied on every point of the surface. So you have a force at every point of the surface, as I said, like the air pressure or water pressure. But here we are start to look at the more simplified case of rather than the 3D force, we are looking at the 2D cases that we have the distributed load. Similar to 3D cases when we have the pressure applied on the whole surface, in 2D the distributed load would be applied on the length of the object. So we have the object in 2D, and then we are going to say that we have distributed load apply on the. For example, if I'm going to have a beam like that, so I assume I have a beam like that, and then there are some the distributed load similar to that apply on that beam. And so that distributed load is a function of x and is in Newton per meter. It is similar to the pressure. Remember, when we are talking about the pressure, we'll say that the unit is the Newton or the force per unit area. For example, said it's a Newton per square meter. When we are using it's in 3D. When we are talking in 2D cases like that, then we say that the Newton the force applied on the unit of length. So we have said that Newton per meter. For example, if I says for the pressure, if I say there's a 10 Newton per square meter, means that on every square meter of that object there's a force equal to 10 Newton applied to that square meter. Similar to that, that's a pressure example. So we have 10 Newton per square meter. Similar to that here for the linear, for the 2D distributed load, when, for example, I said there's a 10 Newton per meter, assume I said that there's a 10 Newton per meter load applying on that beam. It means that on every meter of that beam, there is a 10 Newton force. So we can look at that and see how much force we're going to apply on that. Most of the time when we have the distributed load like that apply on beam, it's not that easy to work with that. So we need to replace that distributed load with a single force. And that single force the effect of that single force should exactly be similar to effect of that distributed load. So again, it's not that easy to work with the distributed load. Because of that, we are going to replace that distributed load with a single force, and we want that single force has the exact effect that distributed load has. To do that, assume that I can replace, I'm going to draw that beam again, and assume I can replace this distributed load with a single force, single resultant force at the position X. So if I want to say that I want to replace that with this, and I want to make sure that this has the same effect as that one, we'll have to find the magnitude of that force, and we'll have to find where that force is applied, where's the position of that force. Again, this is the real case scenario. When you have the distributed load, we will simplify to single force or a couple of single forces to make it easier to analyze our cases. So that's why we are doing that. So we have distributed load, simplify to single forces, and it will make it easier to analyze that cases. Again, when we wanted to simplify it to single force, we need to know the magnitude of that force, and we need to know the position of that force. The magnitude of that force is, if I want to say that the magnitude of that force is, if I want to write it out, it's going to be dA, or it's going to be it's going to be the 0 to L, 0 to L, and assume the whole length is L. So 0 to L. And if you look at this integration, is basically is equal to the area. So it's the dA is the dx and the area. So the magnitude of that force, that distributed load, is equal to the area underneath of that load, because we are integrated. What we are doing, we have integrated all the loads along the length of that load. So we add all the load along the length of the load. If we add all the load along the length of the load, basically what we are doing is we are calculating the area underneath of that load. So the magnitude, to find the magnitude of the load is very simple. Just find the area underneath of that load, and that's the magnitude you have. And for the position where it's going to apply, the position of that load is going to be the integration of x dA, or the integration of dA, again 0 to L, 0 to L. And if you look at this one, again it's going to be 0 to L, x dA, and this one is just A. So we already have it here, so this part is A, and the dA is going to be Wx dx. So dA is Wx dA is basically, this is the dA as we have it here. This part is the dA, and it's times by x, and this part is A. So we use this integration to find the location of that force. How we find the location of that force, how we come up with this magnitude is basically, we'll say that the moment this force created about any point, let's say about this point, the moment this force created about this point should be equal to moment this distributed load created about this point. So if I gonna, for example, call this point, let's put something that will not be confusing. Assume I'm calling this point B. So the moment the resultant force created about point B should be equal to the moment the distributed load created about point B, and if you equalize these two, that's what you're gonna get. So I'm not, so you can write it yourself, the moment of this force about point B, and make it equal to moment of the distributed load about point B, and make them equal, then you can find this distance, and this is how you are finding. This is the general case scenario, that when we have some load on the beam, and this is how we are going to do that. But Generally, most of the load we are gonna have in our problems in statics, they follow a simple geometry shape. And if it follows the simple geometry shape, we can simply find the area of that shape, and we can find that area. This point, in reality, this is the centroid of that distributed load. So this is the centroid of that distributed load. That distance gives the centroid of that distributed load. One more time, if I want to say I have a distributed load and I want to replace it with a single force, and I want to find the magnitude of that single force and the position of that single force, so it makes it much easier to analyze it rather than that. So we want to replace that with a single force. When we want to find a single force, we need to find the magnitude of that force and position of that force. The magnitude of that force is the area underneath of the load. The position of that force is the centroid of that distributed load. So if we find the area of that load and the centroid of that load, we can replace it simply with these two cases. Now, there are, as I said, most of the time we have a simplified scenario. And two main scenario that we are going to have is if our load is going to look like a rectangle or our load is going to look like a triangle. So if you have a rectangle load, I'm going to put here, so assume I have a rectangle load. So assume there's a rectangle load, and assume the length of the load is L and the height of the load is H. Then the area, the FR, is equal to the area underneath of that load. So the area of that rectangle is L times H. L times H, so it's LH. So it's going to be LH. So that's that is the resultant force. So the area underneath of that force, and where that force is going to be applied at the centroid, and the centroid of the rectangle, we know that the center of the rectangle is just right in the center of that rectangle. So this is the centroid of the rectangle, so that's going to be X. And we know the centroid of a rectangle is right at the center of the rectangle, so it's going to be L squared. So this is one case that I want you to always remember. If you have the load look like a rectangle, that's the force. So when the area underneath, if the length of the load is L and the magnitude of the load, we assume the magnitude of the load as the height of the load, and the magnitude of the load is H, so the area under that is LH. So that's the magnitude, and where it's going to apply it? Right in the center of that triangle, rectangle, and center of rectangle is just half of its length. The second case that I want you to remember, if I have a load of like that, and I have a triangle. Again, if the if this length is L and this base is H, so the magnitude of the force is H here, and the length is L. The same thing, the area, the magnitude of the force, the resultant force, is the area underneath of that triangle. So assume we have triangle with length of L and height of H. If there is the magnitude of the force and it's the length of the force. So assume we have triangle with length of L and height of H. So it's going to be half of LH. So that is the magnitude. Just the area of that triangle. That's the magnitude of the force we have. And where it's going to be, the X is going to be, assume I calculate the X is going to be 2/3 of del L. So the centroid of rectangle is going to be somewhere here, and that distance, we know that the distance from here to here is 2/3 of L, and from here to here is 1/3 of L. If we assume the whole length is L, so if the whole length is L, so it's going to be 2/3 and 1, so basically is 1/3 from the base. So the centroid of the rectangle is 1/3 from the 2/3. So if I consider this one as X, so that okay. So we are going to look at some examples so we learn how to do that. But one more time, if you have a load look like a rectangle, the resultant force is just area of that load, and the area is the length of the force times the magnitude of the force, which is going to be its height. And it's load applied at the centroid of that rectangle, which is going to be right at the middle of that rectangle. So it's going to be, again, so X is going to be L over half. The same if you have a load look like a triangle, the same, the force, the resultant force is area of that triangle, which is going to be half of the length times the height, half of the length times the height. And where it's going to be applied, the position of load is at the centroid, and the centroid of the triangle is 1/3 from the base, or 2/3 from this one. So that's going to be the length of the the position of the resultant force. So I want you always remember these two cases, and we always try to use these two cases. So if we have either of these two or combination of these two, we can always use these equations and to find the resultant forces rather than using this method. We only use this method if we cannot find the resultant force from one of these two simple cases. But as I say, in majority of time we can use either of these two. If we cannot, if there's no way that we can use either of these two, then we have to go and do the integration. Otherwise, try to avoid do the integration and calculate it directly by calculating the area and the centroid of that geometry shape, rather than calculating the area and the centroid by integration. If there's no other choices, then we will do that. So now let's look at some simple example to get better understanding of how we do the calculation of the distributed load. Let's start with, assume I have a beam with a 10 meter length, so it's 10 meter long, and I have a load on that, and it's going to be 2 Newton per meter. So I want to replace that distributed load with a single load. So what's going to happen is that I'm going to again draw that beam. So I want to replace that load with a single load, and I want to know the magnitude of that load and the position of that load. So the magnitude of that load again is the area of this rectangle. So the length is 10 and the height is 2. So that's a 2. So the magnitude is your height. So the height is 2, the length is 10. So the magnitude is just area. The area of that rectangle is 10 times 2. So it's 20 Newton. So the magnitude is 20 Newton. And where is going to apply? Again, the centroid of the rectangle is right at the center of that rectangle. So if I want to apply that, I'm going to have the load is going to apply right here, and it's going to be 10 times 2. So this is the magnitude, and the location is just 10 over 2, which is 5 meters. So I can replace that with this, and then whatever I want to do with that problem, do it with this. So whatever analyzing I want to do there, I can start and do it with this one. So the area underneath of that triangle is the magnitude, and the position of the centroid of that that rectangle. So the area of rectangle is the magnitude. The centroid of that rectangle is the position that force would be applied. Now let's look at another example. This time again, assume I have that 10 meter long beam. So it's going to be 10 meter. And this time I have a rectangle force like that. And assume that force is, let's say, 3 Newton per meter. Now I want to replace that with the single force. Again, the magnitude of the magnitude of force is just area underneath of that distributed load. I have a rectangle here, so the area of that rectangle is half of the length times height. So the magnitude here, the magnitude at this point is the height, and this is the length. So half of the 10 times 3, so 10 times 3 is 30, a half of it is 15. So the magnitude of the force is going to be 15. And where it's going to apply, when that point is going to apply, is at the centroid of that triangle. The centroid of that triangle is 2/3 from the start or 1/3 from the base. So if I want to put that, so I know the force is going to be the magnitude for the area under that area of that rectangle. So it's going to be half of 10 times 3, which is going to be 15 Newton. So I have 15 Newton force, and where it's applying is going to be 2/3 times 10. So it's a 2/3 times, so it's its location and its magnitude. So just the area of that triangle is the magnitude, and location of the centroid is the location that the force is going to be applied in that location. Let's look at another example. Sometimes we may have a combination of these two. So let's have that 10 meter, assume that's the 10 meter long force, and this time assume I have a force of, for example, so 2 so it's a 2 Newton per meter for the length of 7 meter. And then right there I have change in the force, and suddenly here I have, for example, a force started from 3 Newton per meter, and it goes all the way to 0. So I want to do that. When I want to do that, one thing I can do is just I go ahead and I say I want to simplify that. So I can go ahead and say I'm gonna divide it into 2 forces. So I have like that. So I have the rectangle forces all the way to here, and then I have triangle forces, just start right here all the way to here. So I have simply divided into 2 forces, so it's a rectangle and triangle, and then I'm gonna find the resultant force for each of these 2. So I say, so assume that's my beam. So for the blue one, for the rectangle, again, I know that the magnitude is the area underneath. So the length is 7 and the height is 2. The area underneath is 2 times 7, so it's going to be 14. Where it's going to be applied? Right at the center of that triangle, right at the centroid of that that rectangle. So that centroid of that rectangle is going to where it's going to be applied. So it's going to be applied here. Its magnitude is going to be, again, the area, which is 7 times 2, it's 14. And where it's going to be? Right at the center of that triangle. So the center of that triangle is the total length is 7, so the center of that triangle is 7 divided by 2. So assume the rest of that is also 3, so we have 10 meter long. Then we will find the equivalent force for this one, for that triangle. Again, the magnitude of the force is the area under that, so it starts from the 3 and its length is also 3, and it goes so let's assume it's 4, so not make you confused. So assume it's the 4 Newton per meter. Let's start from 4, so it's going to from 4 to 0. So the area underneath of that is the length is 3 times 4 and times half of it. So 3 times 4, 12 is 6. So the magnitude is 6, the area of that triangle. So it's a 4 and it's a 0. So, and the length is 3. And where it's going to apply, look at that, it's like this one, but it's flipped. So it's going to be 1/3 from here or 2/3 from the other end. So I'm going to draw that here. So the magnitude is half of length times height, which is 4. It's going to be 12. So that's the magnitude. So this is the magnitude of that. So it's the area underneath of that rectangle. Where it's going to be 2/3 from here. So 2/3 from here. So it's going to be 2/3 of 3. So that's the distance that it has it from that end. So it's a 2/3 from. So we can simplify this into 2 separate shapes, and then we calculate the area for each of the shape, and then the centroid of each of the shapes. So we can simplify that one to these 2 forces. So that distributed force can be simplified into a simple one like that. Again, remember, this is the area of that blue rectangle. This is the area of that green triangle. This is the centroid of this blue rectangle, and this is the centroid of that green triangle. Now let's look at another example. Assume we have that, again, we have that 10 meter long beam, and this time we have load applying like that. Assume it starts from 4, well, let's say, assume it starts from 5 Newton per meter and end up at 2 Newton per meter, and the total length is 10. Again, to calculate that, I can divide this trapezoid into the rectangle and the triangle. If you know the area and the centroid of trapezoid, you can use that, but sometimes it's much easier to just split it to rectangle, triangle. How I'm going to do that? So I'm going to say that I'm going to assume that's what I have. So I'm going to assume that I have a triangle like that, a rectangle like that. So it's a 2. So it's a 2 Newton per meter. And then I'm going to assume I have a rectangle sitting on top of that. like that. And assume this part is going to be 3 Newton per meter. And so this bottom part is 2. It's 2 Newton per meter. That's the 3, 2, so it's total 5. And so I split that trapezoid into the rectangle, rectangle and triangle, and then I'm gonna calculate the resultant force for these two. So I want to find the simplified resultant force for those. This I'm gonna find it. So I start with the blue one, with the rectangle. So the rectangle, the resultant force is the magnitude of resultant force, the area underneath of that force. So the height is 2 and the length is 10. So the length is 10, the height is 2, so it's a 10 times 2 is 20. So it's the magnitude. Where it's going to apply it? Right at the center of that rectangle. So it's going to be right at the middle of here. So you're going to have this one here, and it's going to be 10 times 2 is 20 Newton. So that is the magnitude, and the distance it has is just 10 over 2. So it's the middle of that. For that triangle on the top, again, the magnitude is the area of that triangle. The area is the height is 3, the length is 10, and it's divided by 2. So 10 times 3 divided by 2, so it's going to be 15. And where it's going to apply? Right at the centroid of that triangle. Again, look at this triangle is flipped right there. So it's the half of the length. So it's a third of the length. So it's going to be third of the length from here. So the magnitude is half of the length times height. So it's going to be 15 Newton. And where it's going to be, the location is 1/3 times 10. So the location is 1/3, and probably this one should be smaller because the length. So this one is 15, this one is 20. So that area of the rectangle, the area of the triangle, the area of the rectangle, the centroid of that triangle, the centroid of the rectangle. So again, we can, if we have the force like that, we can again split it into known shape, and then to find the magnitude, we calculate the area. To find the location, we find the centroid of that shape, and that's how we calculate the we basically replace the distributed load with the single loads or series of single loads, depending on how the shape is. But sometimes, as I look at another, so sometimes we may not be able to do that, and we have no other choices unless we do the integration. And let's look one example with the integration as well. So assume I have a beam. This time I'm going to assume I have a beam with a length of 3. Assume the total length is 3. And assume this time I have a distributed load like that. And the magnitude of that load is going to be, let me see what I have. Good. 2 times x cubed, so the Newton per meter. So this time we cannot use any of these familiar shapes. So we have to do the integration to find that. Again, remember to find the load. So we want to simplify that into simple force like this. And we want to find Fr, and we want to find the position of that Fr. So we want to replace it with single force. The problem is that because it's not a known shape like those shapes, we have to do integration to find that. So I'm gonna write that here. So if we look at that, if you remember, again, the same thing, the magnitude is just the area. The magnitude is the area under that load. It's always the area. If we have the known shape, we can do it directly. We do it. If we can't, we have to do the integration. So we are going to do the integration here from 0 and assume that's a W and that's the X. So it's a 0 here. So we're going to start from 0 to 3, and the area was this was the equation. So the area underneath of that curve. So simple integration. So it's going to be 0 to 3, and it's going to be 2. So then the FR would be 2x4 divided by 4 from 0 to 3, and it's going to be 2, 3 power of 4 divided by 0, 4, 4. And if you do the calculation, we'll get 40.5 Newton. So the magnitude of that is 40.5 Newton, and it is the area underneath of that curve. Whereas the location, remember the location was integration of that again. We have x dA and the dA, and remember this one is just the area. This one is the area. We already calculate the area. So I'm going to write it here again, 0 to 3, and x dA, and this is the area. So we already calculated the area, so make sure that you're not recalculated again. We don't need to do that. We already calculated that. And the dA is Wx dx. So that's the dA. So I'm going to just substitute there. So it's going to be 0 to 3 x, and instead of dA I will put Wx dA, and here is area. So I'm going to replace them with 2, and so the 3 is x, and Wx is 2x cubed d. Sorry, that's a dx, not dA. So Wx dx, so it's a dx, and the magnitude of the area is just 40.5. Draw the line here, so make sure. So again, if I do that calculation, I am going to have the 40.5 here, and here I have 2 I have 2 as x divided by from 0 to 3 divided by 40.5, which is going to be 2, and going to be 3, 5 divided by 5 minus 0 divided by 40.5. And the magnitude is going to be 2.4 meters. So I do that calculation, that's going to be 2.4 meters. So if we have the known geometric shape, we calculate the area of that geometric shape, and this is our force, and the centroid of that geometric shape is the location that force is going to be applied, and we can replace it with single point. If we have a case like that, that we don't know the area, we don't know the centroid, so we do the integration, we find the area, and the area is the magnitude of force, and we find the centroid from this equation, and the centroid is going to be the position of that load. Again, remember, anytime that we have the distributed load, we will replace it with a single or series of single forces, and then we start analyzing whatever we need to do. And the magnitude of the force is area underneath of that load, and the location or the position of that single force is the centroid of that distributed load.